Excellent. Hello, everyone, and welcome to one of our TMB sessions, the first one of this week. Together with us, we have Nicolas Kuske, who will be presenting on what rocks can teach us about agency. Apparently, quite a few things. Exploring thinghood through the free energy principle. A few things about Nicolas. He's a postdoctoral researcher associate at the Center for Brain and Cognition Research and the Artificial and Natural Intelligence Toulouse Institute in France. And he actively explores the intersection of artificial intelligence, cognitive neuroscience, and consciousness science, which is quite the CV. So Nicolas, and for everyone else, the structure is roughly this. You have about 40 minutes, give or take 10 minutes, to present. Then there will be a Q&A from the audience, which can last of about half an hour. And then there will be a summary and extended discussion by Carl. So that's usually our template. And the meeting will be recorded. And it will be posted on YouTube as unlisted, so inaccessible to anyone else except those who want and have the link. So without further ado, Nicolas, the floor is yours.
Thank you so much, Robert. Yeah, it's an honor to be able to speak here today in front of all of you. And yeah, so let's see if rocks can actually teach us something about agency. So first of all, what does it mean to be a thing? So I'd like to start with a thought experiment. So imagine we randomly partition space-time into arbitrary regions. So then we could call each of these regions a thing. But this definition doesn't get us very far. So most of these so-called things wouldn't persist in any recognizable form, nor would they be distinguishable from the space around them. So let's refine this idea. So a thing at its most basic is a bounded system that interacts with its environment in a structured way while maintaining its internal states over time. So under this definition, both a rock and an animal qualify as things. A rock has a clear boundary. It responds to external forces like temperature or pressure, and it persists as a coherent structure. An animal, while far more complex, also has boundaries and interacts with its environments in an even more dynamic and adaptive way. But not everything fits this definition. So again, like a random volume of air, for instance, has no clear boundary or structure. It's diffuse, its interactions are chaotic, and it doesn't persist as a coherent entity over time. So this definition gives us a starting point. So under this definition, both a rock and an animal qualify as things, but they differ dramatically.
Sorry to interrupt you. Yes. Are you also moving through the slides, or is just this you're talking on the introductory slides? Because the slides are not moving, or at least I don't see them moving.
Oh, wait, what is it first? Still the first slide?
It's just the first slide, yes.
Okay, and now?
Still the first slide, at least to me. Yeah, seems to be still the first slide. I can see your mouse moving, but I maybe press F5. Try pressing F5.
Wait. Like this. Anything. Okay, I tried to press F5 with a couple of things, but it doesn't really help.
Try the slideshow.
Yes. It's on the tabs, around the middle in the tabs, where you have file, home. That's where slideshow.
Yeah. So you want me to end it?
No.
Now something changed.
Yeah, we're now saying, what does it mean to be a thing?
Yes.
Okay, interesting. Okay, and when I now do this and this, do you now see a picture?
No, I think you must be sharing a window as opposed to, we're still seeing it in sort of editing mode as opposed to screen share.
Ah, okay. Yeah, maybe then I do screen share. Okay. Stop sharing. Where are we here?
Yeah.
do entire screen. Share. So.
Okay.
Oh, God.
Yes. Now it seems to go. Try to change a few slides.
Okay.
It works.
Okay. And just to see, because it would be nice if I would see my thing. So if I go in presenter view, you also see the presenter view, like you see my notes and everything?
Yes, we also see your
Okay.
notes.
Okay, that's maybe annoying. Then let's do it without the notes.
Maybe on display settings. Just try display settings one last time. Up, go up, near end slideshow. Just try display settings. Yeah. Okay. So sorry about that. It's weird that we see the.
Yes. Wait, can I try one more thing? And
Yep.
then. Okay, I just want to try one more thing. Window agency. Actually, like this. Okay, now. Like this. Like this. Okay, and now?
Now it seems to be good. We don't see your notes.
Okay, and the slide has changed.
What does it mean to be a thing? Yes, but without the pictures.
Okay, now there's a picture.
Yes. Excellent. Go on.
Perfect.
Okay.
Yeah, so I needed to actually open the presentation in presentation mode, and then I have two windows, so then I needed to choose that window. Okay. So we have this definition, and now so the question is, there seems to be two categories of things, and this is inert and active matter. And so the typical example would be like a rock, or so this category, so this is like an archetype. So this category also includes objects like tables, Eiffel Tower, even atoms. And so these systems that do not autonomously interact with the environment in a directed or adaptive way, at least it seems like it. On the other side, we have active matter, so bacterial cells, which serve as our archetype here. And this category also includes animal, humans, but also plants and individual cells. So systems that exhibit some form of autonomy and adaptability in their interactions with the environment. So the boundary between these two categories, between inert and active, might seem obvious at first glance. But if it's so obvious, then it should be easy to find an objectively definable measure, which is like which can be defined in mathematical and physical terms. So this is what we want in science, right? We want to really see, do our intuitions hold up to mathematical rigor? And so maybe one simple idea would be where we just define active matter as a thing which can autonomously move its center of mass. So well, this would mean that rocks and basically all the things on the left, they are inert. However, there's also a large class of bacteria which are non-motile bacteria, so they don't have any flagella or papillae, or how it's called, so they cannot move around. And so they cannot move their center of mass by themselves. So that would also, so this definition would also say that they are inert. So, and moreover, interestingly, there's something called Janus particles, which are like two spheres with different properties, asymmetrical surfaces, and so if under certain conditions they can react, one side can react, and then this particle would move through its environment. But few would argue that this is a truly an active. This really means that this is active matter in a meaningful sense. So then, what is a property that truly distinguishes active from inert? So what is this hard, physically measurable property that separates these two categories in a way that makes sense across systems? So this definition is not sufficient. So here I propose adaptability as a minimal criterion to distinguish active from inert matter. So adaptability, to define activity, we need to identify a system's ability to undergo self-organized changes in response to internal or external conditions. And crucially, these changes must serve to preserve something essential about the system. So there has to be a norm that identifies it as the same thing over time. So what do we mean by norm? A norm is a state or set of states that define the system and persist throughout its interactions with the environment. Only if they persist, the system is still itself, so to say. So without a norm, there's nothing for a system to adapt to or preserve, and thus no basis for calling it active. So then adaptability can be defined as a self-organized structural change that preserve its norm, in the face of internal or external challenges. And this is what separates activity from mere responsiveness. But this definition has even deeper implications. So if we look at this simple diagram here, we have an external state and the system, and the external state has an effect on the internal state, and there is some norm state. We do at this point we don't further say how this norm state how this norm state is known to the system. At this point, this is a conceptual illustration. So there has to be a norm state, and this is compared to the current internal state. And then this comparison leads to an action. And this action then adapts the internal state and possibly the external state, so that the next internal state will be closer to the norm state. So this would be a rough conceptualizing. And now we can actually see that this definition of an active matter or thing is equivalent to calling it a self-sustaining agent if we say that an agent, in order for there to be an agent, this system has to be a goal. And since this system is constantly so the system's internal states are direct towards preservation of the norm. So it's constantly acting towards preserving this norm. This can be statistically identified then as a goal of the system. So in other words, an active system is not just adapting; it's adapting for purpose, and this is self-sustaining. So then if we say that an agent, that's sufficient to define an agent if it has some goal state, then we can say, okay, actually this definition of activity is equivalent to saying there's a self-sustaining agent. So active matter, self-sustaining agents. We have seen that so this is like a rough outline how this could look like, but so far we are still missing like really mathematical rigor. And so for this, I want to introduce now agency as we define it here, and its relationship to free energy minimization. So in the last slide, we proposed adaptability as a defining property of activity. And showed how it refers to how it coincides with agency. And now we turn to the free energy principle. So recall again, we have a comparison of the internal state and the norm state, and the difference then leads to action that will minimize this difference. And the free energy principle is based on the idea that that systems that persist over time, so things, they can be defined as systems that minimize their free energy, and this means that they act as if they want to be in this norm state. So the difference from the predicted norm state. So here before we have seen that we don't really know where this norm state is coming from. So how does this system know what its norm state is? So the idea in the free energy formulation is that we have we have external, sensory, internal, and action states, and the internal state describes a generative describes a generative predictive model which has information, so which embodies, so to say, the norm state of the system. And now we can so free energy measures the mismatch between what the systems expect based on this model and the sensory input it receives from the environment. And then so this process allows the system then to persist as a coherent entity, because this coherent entity means that these norm states will persist over time. And this distinguishes it also from the surrounding environment. And the key insight here, which is important also for us in our definition of agency, is that it doesn't just define things, but here we with our definition of activity, we have here that this is also a self-sustaining agency. So that means that under the free energy principle, the definition of a thing is mathematically identical to our definition of a self-sustaining agent. And on the next slide, we'll explore this mathematical foundation and see how it actually maps onto real physical mechanisms and not just diagrams with arrows, although diagrams of arrows will appear again as well. So yeah, so the mathematical foundation rests on the idea that you can that you can have causal graphs, and these causal graphs they have structures such that certain variables are conditionally independent of other variables, and that means that these variables shield. So the probability for a certain so if we look at the the probability for a certain variable to have a certain value is equal, given all other variables, can be is equivalent to saying, okay, the probability, we can also derive this probability for the particle to have this specific property, just given all the states of the Markov blanket of x of the specific variable. And the Markov blanket means is basically the environment of this event, or of this part of the system in terms of the causal graph. So really, I mean, this can be an abstract mechanism, but in simple cases, it can be really mapped onto the topological, like the simple structure which we would imagine if there's like really nodes like this, depicted here in the diagram, if they're really structured like this in the world. So yeah, wanting to say, so like if they're close to each other, then they can be thinking of shielding other parts of the system. In the simple case, as I said, one can also think about systems which are where physical closeness does not directly correspond to a causal relationship. If we think of remote controllers or stuff like this, but yeah, for now this should suffice to understand what we mean. And so we can using this this Markov blanket framework, we can then define a system with respect to its environment. We can partition the system and the environment, and we can partition the system into internal states, which are shielded from the environment through the sensory and active states. The sensory and active states are still part of the system, so they are still part of this thing. And then we can so the free energy. We want the system to minimize this surpriser, this free energy, and so it how do we explain it? So in this equation, the logarithm of q is the expected value of the logarithm of q is the expected value of the logarithm of the approximate. So this q is the internal approximate model of the external states. So the q is the model the system has, and P is the actual distribution, which depends on the internal state and on the actions of the system. And so we want this to be 0, and we can minimize this free energy through two different pathways. So one would be active inference. This means that we act on the environment, and the environment then leads to a different sensory state, and if this sensory state is what we so we can act such that this sensory state is closer to what we predict. Then we minimize this surpriser. So this would then be an active inference in the way that we act on the environment to minimize our surpriser. The other way would be perceptual inference. This means that we it's not an action on the environment, but it's so to say an internal action of the internal model which predicts the norm of the system. It can change its own state, and so basically it changes what it predicts, what it thinks the norm of the system is. So at some point, I don't know, if I grow up for example, as a human being, if I grow up and I've never tasted something really good to eat, then I expect then I'm not seeking for something good to eat. But when I then finally eat something good, my internal model updates and says, "Oh wow, actually this is what I now understand that I want this. That this is actually my norm. So seeking of so I am more myself when I can eat something which I like in this sense." Then, So these are the two ways: adapting the internal model or adapting the environment. So acting in the environment. Which can be related. In my example, they were now somewhat related, but they can also be looked at as there are also ways in which they can be independent. yeah, for example, simply if I am hungry right now and I'm going to find something, then I'm not changing my internal model, but I'm seeking. So if I then find something to eat, then my internal model is satisfied. So yes, yeah. So these are the two ways I can the mathematical framework of the free energy principle allows, together with Markov language partitions, allows us to define how this system can interact with the world such that it follows our criterion of adaptivity. So we have established that. So now I want to introduce something which might be a new kind of action. This is which is active sensory inference. So what does it mean? So we have established that systems minimize free energy through perceptual inference, updating internal states, and active inference where actions modify the environment to align sensory states with the internal model. But what if there's another kind of action? So one that targets sensory states directly rather than indirectly. So if we look here at the simulation of particles that automatically formed together so that we have so they build a kind of they're similar, they resemble a simple bacteria, so to say, but then in the simulation, the external states would be cyan, and the sensory states would be the pink, and action state would be red, and the blue would be the internal states, and this can be mapped so to cell walls and internal cellular compartments of a simple bacterial cell. However, this is a way you can map this onto a physical system. However, it can happen that there's suddenly an increase in so if there's suddenly an increase in an acidic milieu, then the bacterial cell has two ways it can react, because it will, so the acidic milieu, it will it will kill the metabolism in the cell. So it has to get, so if it gets the same if it gets the same density in the cell as outside of the cell, then the cell will not survive. So it has two options now. This collective Markov blanket system. It can walk away, like it can do active inference and move away. But if it cannot move away, so if it's a non-motile bacterial cell which cannot move its center of mass, then it has to find another way to survive. And this cannot just be perceptual inference, because it cannot change its internal model as much as it doesn't exist anymore. It needs its norm state in order to, like, we define norm state as something which so that we can identify the system. And if the system dies, then this norm state will not be satisfied anymore. So perceptual inference, updating of internal models, is not enough. So it cannot move away. It cannot act on the environment to reduce its surprisal error. It can also not do perceptual inference to reduce the surprisal error. But it can do something else. And that is, it can directly we can do this in a moment. It can directly, so it can actually change. It has some, so ADP and adenosine triphosphate pumps which can change the direction, and it can actually help pump ions out of the cell membrane. So in this sense, then we have so again, yeah, no, we saw this. So yeah, so we can active inference is not possible. And perceptual inference it can do perceptual inference, but it will not save it. But so there seems to be this new kind of this process, this action, which directly acts on the sensory state by so the sensory state says I'm too acidic, and then the adenosine phosphate so these enzymes, these molecular mechanisms, they adapt their structure so that now because of the sensory state representing a mismatch to what it should have, a mismatch to what it predicts, it will now automatically activate a process such that the sensory state is changed, but and this will also affect the external state, but it will not affect the external state in a way such that it helps the system to reduce its surprisal. It just pushes more. If it pushes more ion outside, if it pushes more ions outside, it does not it does not change the environment to so that less ions come inside. What it does is it really affects the sensory state directly through an interaction with the outside world. But it's not that the outside world changes such that the sensory state now resembles so the sensory state is coupled to the outside world. The sensory state represents in this sense the outside world. But usually active inference through changing the environment would be, okay, I change the environment such that now my sensory state is such that I want it to be, so that my predicted sensory state is so that my sensory state is close to the sensory state I want to have in order to survive. But this mechanism, what the cell is doing, I'm asked, it's basically a question, but I think it's something I want to purport here. This mechanism now is not changing the changing the external state such that it then changes the sensory, such that then the coupling to the sensory state leads to the reduction of free energy or surprisal or prediction error, but rather the change of the sensory state directly. So it's a specific kind of action which acts, which, so to say, changes the internal the body, the milieu in a way. Yeah. So so this is, we see this still needs to be some better formalized maybe, but I think this might be something, a new kind of action which does not fit in the normal active inference idea. It's maybe it's related to interoceptive inference in a way, but since it's yeah. So I just want to say there's some action which changes and something internal to the system, and through this internal change, which is not a change of the internal model, it minimizes free energy. Okay. So can this so there's a nuanced strategy for energy minimization here. And yeah, this is so the question is now, can a rock be an active thing? How does this relate to what rocks are doing? So in general, what one would think, okay, there's an external state. If we want to do a partition of a rock, then we can say, okay, there's this environment, and there's our rock, which has the surface, which is the sensory state. And if the environment changes, then the sensory state will change, the internal state will change. But the rock can neither change its internal model, if we want to say it has such a thing, but we come back to that in a second. And it can also not act in the way that it changes the environment, such that, or at least not obviously, it cannot change the environment in a way such that its prediction error would be minimized. So why would it even? What does it even mean? So how can we even define a prediction error with respect to a rock? So we can say a rock. If we hit a rock with a hammer, then there's under certain conditions this rock will break. If it's very cold, for example, so it needs to have a certain internal temperature. It also depends on certain structural properties of the rock, physical properties. So let's say we have a rock, and we hit it with a hammer, and the rock does not break, but rather so it would keep it will take in the energy, and it will distribute this. So we can define the sensory state as the part of the rock which is which mediates the influence of the external force on the internal states. And then we will have then the rock will distribute this energy. So we have the energy will be dissipated outward through heat or deformation or resonance properties. We can imagine different kinds of nonlinear dynamics in the rock, which all all of this happens within the rock in its eternal state. But when it comes to the surface area again, then we can say, okay, the surface area now changed to become really active state. So in this sense, then in the rock is a dynamic, is different from the systems we have analyzed before, because for the rock, the sensory and the active state, they would be spatially identical, but only temporally. So they would only be different in time. We needed the temporal aspect to distinguish, to make a real Markov, to make a real partition of the rock into our well-known structure, such that we can then say that the rock fits into the free energy principle. And so again, we see that the rock cannot adapt its internal model, but it acts. So I mean, do we even want to talk about an internal model? Well, so far, all that we have, I mean, they have been, we have seen the system which we have seen as I have evolutionarily developed so that they have mechanisms which embody the ability to predict sensory states which are close to the norm. But the rock has not evolutionarily developed. Nevertheless, it does not appear out of nothing, but it's still a process which was a conglomeration of different basically dust coming close to each other, always getting I mean different pressure gradients and so on. So this is this is a highly complex process which formed the bonds of the rock, and I even want to say maybe complexity is not the important thing here. What is this? No, okay, everything is good. Oh, what did I do? Okay, sorry. Do you still see my slides?
No, we only see you.
Okay. Ah, yeah, this is how I do it. Okay. Okay. Oh, fuck.
Now we can see them.
Okay, so very good.
Yeah.
Okay, so I was at the rock.
Yes.
Do it this way. Okay. So yeah, so maybe complexity is not even some. So people often say about, we need a certain complexity in order for something to count as this or that. But I think that complexity is, again, it seems to me like a word which is trying to hide something. So what do you mean by complexity? If you want to talk about a certain mechanism, then explain to me the mechanism which you mean. And so all we can say at this point is that the rock statistically seems to fulfill these criterions so that we can talk about an internal model. I mean, yeah, given that we find a way to put this dynamical Markov blanket partition into a more formal, rigorous light. But given that this is possible, then we can say, okay, it has an internal model, but it cannot adapt it, and it cannot. The rock can also not do active inference. It cannot do active inference in the way that it changes the environment such that its sensory state is how it should be. However, it can do something which is similar to what non-motile bacterial cells can do. Namely, it can change its sensory state through distributing the energy which changes the state which it predicts. It can distribute the energy such that such that at the end of this distribution process, when the energy is distributed into the environment, that it is close again to its norm state. So it does some kind of homeostasis in the sense. Okay, so this is an interesting comparison. And now, so this is actually already my last slide. So why should we care? This is just a terminological difference. Are you wasting our time here? So I think, first of all, we really have a probabilistic formal starting point. And why start here? So I'd like to cite Tristan and colleagues here. So because the only thing we have at hand to really understand a system, to map it to linguistic terminology, is a probabilistic description of the system. In the end, that's really all we have. And so this is what we want to work with. And I think it's important that we have this kind of formal approach so that we can go beyond human-centric views, beyond. So sometimes intuition is a great thing, but usually intuition means, yeah, I've done a lot of very similar things, and now I can rely on my intuition to in the same context to make a great decision without thinking much. But if we talk about things which we don't have a lot of experience with, because we usually don't think about these kind of things, or we don't interact with them, or they are very different from our normal topics, from our normal structures, then a human-centric and anthropocentric view, similar to views, to other heliocentric views or others. So the point is that this human-centric view biases understanding of agency, cognition, intelligence, and even consciousness. And I believe that we are at a state and time where we can go away from these I almost want to call it a little bit, I mean, I don't want to go too close to any, I don't want to call someone out, but I think it has a little bit of arrogance actually to think that this is like, we are the measure for everything. Yes. So I think having a mathematical probabilistic theory, formal theory can help really in understanding these concepts. Furthermore, if we look at this example can really may have applications across scales. So if we look at other homogeneous ensembles, for example, in a non-hierarchical multi-agent context, if we have a group of friends interacting, they are loose. They might, or let's say, just imagine you're sitting in a room and you're talking to other people which are also sitting there. They're not moving. Suddenly from the side there comes a loud noise or something. How do the people react? Is this similar to how can this be mapped somehow to maybe to how a rock would react? Or so like this kind of non-hierarchical multi-agent systems. Also from not if we look at artificial agents. I think there might be so we might be able to map very simple systems to seemingly very complex systems. And yeah, so this scalability is something which we want to take, which might be something which we can use, which we can leverage in the future. And finally, I think the probing the borders of categories is especially important if we believe that these categories are really important, that we want if we want to really, for example, if we want an intelligent system or we want a conscious system, and we believe that that these are categories which exclude certain systems, then I think it's then by really probing the borders of the categories, so something which I did here, probing the border of what agency is, then this can help us to really find the property which is the specific property which we need for a certain to understand and to maybe build systems and to build theories and to understand certain categories. Yes. And yeah, so I think this is what we did here today. I think it's more than just terminological hair Spalterei. Yes, and I think this, I don't know, it was very short, I guess, but I think this yeah, I would like to discuss this with you and have your feedback on this. And I'm very happy that I can talk about this idea with you.
Thank you, Nicolas. So we invite everyone to unmute and give Nicolas a round of applause for his talk. Also, digital hands go a long way. All right, so now we open the floor to questions from our audience. If there are any questions of any kind of type or kind, and even strange kinds. All right, so I will kick off by saying I fully agree with your conclusions in the last slide. I think that's a very positive outlook to have on how we should approach more than one issue that we are dealing as a research community and as a science, or ultimately many sciences as many fields together. So with that being said, I would want to ask you something about more of the technical details of the view you are proposing, which, as far as I understand, it's you're trying to find an intermediate form of action that would not be fully agentive in the sense of the path integrals, particular kinds, and strange particles paper. So paper, rocks would be there, definitionally simply inert things. And while you can still read off um, the dynamics of the internal states as inferring or as having beliefs about latent external states. So basically, you can still apply the entire formalism of active inference under the FEP. That doesn't mean it is, I would say, a form of sentience involved there. So there is a quote in the paper where they say that sentience, and in the form of active inference, is a prerogative only of active particles. So particles that have active states. So what you're trying to do is to find an intermediate kind of ground between no action and action, and where you would put rocks as having some form of, I think you called it interoceptive action, where you, or something like that, where just the sheer distribution of energy that they would have in virtue of an intervention from the environment. So like the, I would say, kinetic energy absorbed from the hit of a hammer, they would distribute it in a way to preserve some norm that describes the structural integrity of the thing, that enables a recognition of that thing as persisting as the thing that it is. So this is in a nutshell how I understood your attempt. But then my question for you would be, what is then the difference between, let's say, an purely, from the rock's perspective, purely sensory process in which, let's say, the erosion throughout millennia at the forces of nature carve out the structure, the outer structure of the paper. So that would be, from the paper's perspective, some form of sensing in which it registers changes in the physical magnitudes in its environments on its surface. So you have that. And what's the difference? So that would be qualified as a sensory process. And what's the difference in kind with hitting it with a hammer? It just happens that the sensory states of the network that constitutes the rock absorb the energy. So the physics at that scale is strong enough. The bonds are strong enough to withstand the pressure, but it would still be, as far as I'm concerned, a sensory process. It would just be the difference, let's say, to give a very bad analogy, I can press it and it's still an eye, and it absorbs the forces of the pressure. But if I shoot something through it, it won't absorb it. But still, the eye doesn't transform itself into a hand. I know the analogy is not good because the eye can also move, so it has active states. But this is just to say that I think what the rock does when you hit it, it's still sensation, roughly understood, rather than action in some way, as the states for actions are not there. So, what do you think of this?
Mm-hmm. Yeah, that's a good question. So I think that the difference between the kind of erosion that you or like other weather influences, but this kind of erosive interactions with the environment versus something like a hammer blow.
Mhm.
I think the difference is that the rock. So this is a little bit difficult to put into quantitative terms, but I would say that since the rock has the ability to, so I can hit the rock with a hammer, and it will. And I mean, so I'm still not a rock expert, unfortunately, but I think if the rock is in a certain condition with a certain temperature, a certain structure, let's say there are rocks which I can hit with the hammer infinitely often, and they will not have any damage from that. So because they will always take in, they will always have this possibility to redistribute the energy and put it back into the environment so that its sensory state goes back to how it should be. And
Okay.
I think there's a difference. Maybe it's the directedness of it's the way. Yeah, maybe it's the directedness of the interaction. It's the strength of the interaction. It's as I said, it's hard to quantify, but I think there's some difference in so with erosion, the rock has no has no way of sensing in the way, like it cannot. It's too it's too so erosion means that a certain local part of the rock will get problems, and I think that the interaction really is limited to this part. So it's not really, you cannot really say the whole rock is responding to this to this to the wind particle at this point if it's not strong enough. So I think that there is there's a distinction between so I think it doesn't even register as a sensory state really. So erosion is caused by a process which if we look at the rock as a system, which do not change the sensory state of the rock. Yeah. So it's similar to like if someone would ever so slowly every day of your life would take a little part of your skin. Well, I mean, that's not a very nice way, but it's like something. It's like you don't even notice it, and suddenly at some point you're like, oh wait, I'm just half the size as I was before. So it's not really it's not a sensory process then. So there's certain processes which can change you, but which will still not be, which I would still not call sensory states, or which do not. So there's certain external processes which can change your structure, but you will still not be able to reply to them because you will not sense them in. Yeah.
I mean, the obvious reply, half jokingly, is that if they would take enough bits from my PC, from enough bits of my skin, and I wouldn't have time to regenerate those, at some point they would hit the nerve endings and I would feel the pain. So that would be a sensory state. And even just feel that the pressure is high enough, the mechanoreceptors should detect it, so it's still a sensory state. So as far as I am concerned, as the agent that I am, whether for the rock it would be different as all these forms of energy transductions are absent. But still, to me, it still seems that it would be purely sensory, if it can be called like that, process for the rock to be hit, whether it disintegrates or not.
Okay, I mean, I'm not sure I understand your I mean, I understand your argument that it's kind of weird that there's that there is mechanical interactions with the rock, or whatever. Like there are interactions with the rock where the rock has the ability to react, I want to say, such that it survives, and there are processes where it's just going to be slowly decaying and it's not even recognizing. And I understand that this is different from other systems, and this might be related to the Yeah, I mean, I don't know. It might be related to that sensory can also become active or something. But yeah, I know it's a good point. It's an interesting point I have to think about. But so yeah, just I keep this as it is and no but. Where I want to disagree, however, is that from that you seem to follow that. So I don't see the relationship of saying so because erosion, what the rock does is just a sensory perception. So this I don't follow the argument.
Okay. I mean, I think if I remember correctly, I think it was in the paper, but I'm not sure. I read the paper some time ago. So yeah, maybe to introduce just a slight distinction, let's say reaction or a reactive response, which can be called a response, can be itself active or passive. So a reactive response is that when someone tries to do something to your skin, you take your hand back. But then a passive reaction would be just lying there and taking it. So in this sense, that's why I think the rock doesn't have any form of active or agentive aspect to it. It's missing any autonomy. So no matter what you do to it, it is bound to react solely passively in virtue of the physical makeup of its constituents and the properties that they have. So
yeah, okay, but I mean, okay, wait. So of course that's true for everything in this universe, but what was the point with the sleeping? I didn't get the sleeping part.
No, I can take my hand away. So the point is that I can react in an active way. So one can react actively and passively, whether that makes sense. So if you can make an intervention on an agent that has action states and they would react to that intervention. Whether you can make also an intervention on a stone, on a rock. And since it doesn't have active states, it will react by just being there passively in virtue of I would say, its physical makeup. So it still seems to miss that special ingredient of action, as far as I can understand it. And it maybe can be read off as sensing. But the fact that we can apply the formalism, I'm not sure whether elicits or warrants us to call it an agent. Presumably it's not, because an agent means it has agency. So I'm not sure whether that's the case. But yeah, maybe I'm missing something, or maybe other people have a better question. And yeah, we can. I understood your point.
Yeah, I mean, I'm still waiting for your mathematical thing that shows me, or I don't know, like a clear argument which says, okay, action means this, and the rock does not do this.
I think in equation 18, in the paper on page 45, then you have the functional form of the variational free energy. On equation 19 afterwards, you have it unpacked for the rock case without action states in the Friston et al. 2023.
Where would that be?
Page 45 of the PDF. So equation 18 and down, equation 19.
Ooh, 43. Okay, I'm 45, and now you say what? Sorry.
Equation. I mean, you just look at the equation number 18. It's on the page with the figure, the nice figure.
Yeah.
So there you have the description of how you would estimate the generalized free energy, variational free energy for the rock based on the machinery of active inference under FEP, but without action, as far as I can recall from a skimming from it. but it would still miss action.
Okay, I don't. I'm not sure why this pertains particularly to the rock and why there is action missing.
Look at the matrices in equation 18. There is no flow for action states.
Yeah.
You have eta, s, and mu for external, sensory, and internal, but there is no active state.
Yeah. So yeah, I agree. But isn't this just because, like, I mean, I'm that because the sensory, the active sensory inference which I define, so I think according to this equation, a cell which does not do active inference would also not do action. No, but
a cell without motility.
Yes.
Well,
I'm just. Yeah.
I mean, I think that a cell would be quite different than a rock, in as much as motility is not the only kind of action you can have, and a cell can do many other things in its internal milieu, as perhaps creating some cycles within as a response, like creating some using basically the internal machinery as a covert response to any external stress. And there is a lot of stuff going on when you expose cells to certain stress, and they reply to it, even though they cannot move. So movement is here not the only kind of action you can do.
Yeah.
I don't know enough biology to invoke some subcellular process that would be I don't know, like pH concentration regulation, like acidity regulation. Maybe.
I mean, yeah. I mean, this example I gave here, I thought so. So as I understand the active inference, it would mean that I change the environment such that I get a sensory state which is according to my predictions, right? Yeah. And so I'm saying that this mechanism which I'm proposing, this sensory inference, or basically just what a cell, I mean, so what a cell does when it, so I mean, a cell has a limited amount of mechanisms it can do, and let's just for the, I mean, I am also not an expert in cells, but if we just look at this, if we just select this particular mechanism that, so the cell is suddenly there comes like an influx, like I don't know, someone puts a drop of acid somewhere, or something, I don't know, and then so the cell, so there's like more and more ions coming to the cell, and the cell would acidify and die if it doesn't do something. But all it does is change the inside concentration, and so this action, it involves the environment because it pushes inside ions to the outside.
Yes.
But it does not change the external environment such that the internal state, such that the sensory internal state is closer to the prediction, but it changes the internal sensory state through internal action. And I mean, it's not totally internal.
That's what you call interoceptive action, kind of, right?
I don't really have a perfect name. I call it sensory.
Yeah.
Interoceptive action is maybe good. I just like, the only thing is, so before I had this idea, okay, maybe there's interoceptive and exteroceptive sensory states, but it was like it's a little bit problematic then with mathematics and the Markov blah everything. So I just kept by saying, okay, we just call it the same sensory state. Maybe it would be clearer. It would be easier if we say, okay, there's an external sensory state which directly represents external stuff, and there's an internal sensory state which represents internal milieu. Maybe that would make it better. So yeah, so my basically my point is that I feel like this is something which is not really expressed in the framework. So if you would just if we would just say, if we just look at this mechanism, if we say, okay, there's a cell, you know, let's just for the fun of it say we build a cell, I don't know, some artificial cell, and all it can do is this. Then I think according to the normal active inference action definition, then it would not be active. It would be a rock basically. Yeah.
Okay. Then I suppose the natural thing for us to do is to wait for Carl to see his reaction to this. active reaction to this.
Yeah. I'm just thinking, is it okay if I quickly go to the bathroom? Or is it...
Certainly, please.
Yeah.
I mean, yeah, we can take maybe a 2-3 minutes break, because yeah, certainly, no worries, please. If you want to, yeah. Carl, may I ask you something?
Yes.
Would you be available to have a meeting? I'm not sure whether before the holidays of in early January with us to discuss some of the things, the TMB chairs we were musing over changing a bit the format of the meetings and maybe making them public. That was one of the big discussions, whether we could have everyone agree to have their meetings posted on YouTube in our channels. We also had a meeting, me and Reeds, with Daniel Friedman from the Active Influence Institute. So the affiliation process is ongoing. So there are many things we would like to discuss with you, and we are wondering what's your schedule for the next, let's say, 20 days.
Yeah, no, I'm very happy to meet. Well, if you identify a time that's convenient for everybody, give me a couple of choices and I will reserve one in my diary. The alternative would be to actually use a TMB slot itself, and then you know that I'll be free.
Okay.
Providing obviously no one else has booked that. So either choose one where you're all an existing TMB slot when everybody is available, and if not, then find a couple of convenient times and I'll reserve the first free one in my diary. Yeah.
Okay. We will do that. Okay.
Lovely. Thank you very much.
Thank you.
One second.
We've got recordings of all the previous ones, haven't we? Somewhere.
Yes.
So they're all archived.
Yes, they're on YouTube. Yes.
Brilliant.
We were also considering whether to make those available as well on a maybe month-by-month basis, but that's a bit more complicated to ask people that maybe delivered the talk 2 years ago.
Yeah.
There are some nuances there, so we are still not sure.
Okay.
All right. So, I mean, without any other questions from the audience, I, for one, have to go in a few minutes. I think it's Carl's turn right now, if I'm not mistaken.
Thank you. Yeah, I'll take over. You've got 9 minutes until Anil's group meeting. So excellent. Thank you very much. And
thank you,
lovely conversation. Cheers.
Thank you, Nicolas. I have to go. Bye.
Thank you, Robert. Thank you so much. It was a dream come true talking about this.
Yeah, I'm happy. It was a blast. I had a blast. Bye.
See you, man.
Bye. Nicolas, can I ask what kind of feedback you'd find most useful? I mean, these are clearly big issues. And have you written this up? Are you wanting to write this up? Or is this part of your research, or is it something you're doing at the weekends? What stage are you at in terms of looking for feedback or comment or guidance on the development of this work?
Yeah, I guess at this point, so it has been mostly weekend work. So I mean, I'm getting paid for putting the global workspace theory onto AI, and I will also probably do some EEG at some other place in the future. But like at the moment, I'm doing some philosophical work also with some philosophers, but like especially on the topic of consciousness and panpsychism, but related to really this free energy. So this argument I presented today, it basically it has been work of weekends. I don't get paid for it. I don't have any paper yet. I mean, I do have like a work in progress, but nothing. So the very argument which I presented today, it kind of basically came up the last days while I was actually just taking my time, to say, hey, I can finally have some people to listen to me, which are actually professionals, and Carl will be there, and I'm just gonna give it everything now, and just a couple of days basically where I delved into this very deeply, and I would love to. So I guess the feedback I would like is like, do you think it's sensible to try to make this into something which one could publish, or what would be your general idea about this whole direction basically of thought? Think it goes to the trash, or
No, I think you should, and assume that you were trying to write, and I presume really in the first instance it would be a philosophy paper as opposed to a technical physics of life kind of paper, but I may be wrong. So no, I would certainly encourage you to pursue this. It is an extremely important area. Probably even more so since the current debates about sort of AI governance and ethics, and what kinds of systems can be sentient and what kinds can't, and how do we develop the right kind of ontology for natural kinds. So I'll give you feedback of the sort that I think would help clarify the arguments, and I'm assuming that the agenda here is to have a more refined definition or ontology of natural kinds of things. And I think that there is an opportunity to do that beyond the strange things paper, which was, had an initial and foundational attempt at these kinds of distinctions, but did not take it to the more fine-grained level that you have taken it to. And I can see ways in which you can certainly do that. So just to, there are a few just very simple things. First of all, I think despite the poetic allure or the poetic attraction of using a rock, I think you would be better making your point if you thought about a football, a ball, that many people would say does not have agency, and yet acts in a way to restore itself in terms of its shape when bounced or hit or physically manipulated from the outside. I think the rock is a bit difficult because the rock does not, when you're describing it to a lay audience, when you hit it with a hammer, you have to say, oh, and it doesn't break and it doesn't change shape, but there is energy flowing around. I think it's much simpler if you use something like a balloon or a sponge or a ball that is deformable and then reactively reconstitutes itself. So it has the norm, it has this characteristic shape, and will return to that shape when reformed. You could use the rock.
I guess I would then take like you said, like a rubber ball, like something which is like a is very simple thing which doesn't have any any holes or anything. So yeah, I think this would be the best. Yeah, I agree. Yeah, that sounds good. Yeah, okay, please. Yeah.
Yeah, you could use a rock, but I think you wouldn't. What I would do is use use temperature. So either use a ball. I think using a ball or a sponge, something that is malleable, that returns. It has it's not quite active matter, but has memory in the sense that it returns to the same shape when deformed. You could use rocks, but you'd have to, I think, use the temperature of the rock as the state, because clearly a rock will adapt its temperature to the ambient temperature. I think the slight problem with that is that there isn't the norm. Whereas I think what you want to get into this is that for every thing, there is some normal state or characteristic states that it occupies, and that certain things will actually return to these characteristic states when removed from them by being perturbed, hit with a hammer, or being squashed, which which, as I say, for a rock, it's I think your story would be much easier if you spoke about a malleable rock. Just in relation to your conversation with Robert, excuse me, I think the definition of things, certainly from the point of view of the free energy principle, just pertains to the temporal scale over which these things possess characteristic states. So you can't talk about rocks eroding or your skin being worn away without it being replenished. So you can only apply the free energy principle over a time scale where these norms or characteristic states define the system in question. So that, I think, will make your argument much simpler. So you don't have to worry about erosion or, if you erode a rock to the point that it disappears, it is no longer a thing. It is no longer a rock. And the free energy principle, and in fact, any mathematical ontology will just not apply because it has ceased to become a thing. So I think just make your life easier and say that you will be talking about things that are separable from the rest of the environment, that exist in virtue of possessing characteristic states that you've called norms, and do so for a non-trivial period of time. And during that period of time, you now need to understand the different kinds of things, or the different categories or natural kinds that could emerge. And then you're going to go through your story saying that there's, there are lots of interesting intermediary kinds of things that go beyond simply the difference between inert things, such as I imagined rocks on the moon, not rocks that you're going to hit with a hammer, and active things. So I'd, if you can, I'd use something that's more plastic and has a memory of its norms or characteristic states as evinced by its response to perturbations. I think that will be a simpler story to tell. The other simplification is that I noticed you had difficulty using the cell example here because, of course, in pumping protons or hydrogen ions into the external milieu, you are changing the external states. I think there's an easier example whereby the internal states, the active states, directly affect the sensory states by increasing their sensitivity or decreasing their sensitivity to the external states. I think that's the kind of covert or internal action that you are trying to convey. And I think that's an important distinction, an important point. So a very simple example here would be closing your eyes. So here's an active state that largely, although it does physically change the external world, but from the point of view of the sensory states, it basically, the main effect is to change the coupling of the sensory states to the external states. And that's an important, if you like, kind of action that is distinct from action that just moves or affects the external states directly. So I'll make some suggestions about how you can generalize that idea to talk about certain things that have overt action and covert action. And I think that's what you were. That's how I read this active sensory inference. It was more covert action, either operating directly on the sensory states or possibly on the internal states, which is another possibility which you haven't spoken about, but I think you should talk about as well. Again, before I forget, active sensory inference, that might be a bit confusing because there is a large literature in neurobiology called active sensing, which is effectively active inference. So I think you need to come up with something that is distinct from active sensing or active inference, active vision, for example. And what you want to get into it is that the action is not on the external states. It's on the particular states of the particle or the person in question. I think that's the big.
I wanted to call it latent active inference, maybe.
Yep. That's yes. I think that would be absolutely fine. It'd be latent from the point of view of the outside. Latent action. Yep. Anyway, so those are my sort of practical points of clarification. But just in terms of helping you build this story, I've got a couple of papers I thought might be interesting for you to think about, just as ideas that I'll quickly run through. So with your permission, I'll grab the screen and just.
Before you start, can I do one comment on this on my why I chose this example for the sensory what I call active sensory inference at this point? Let's call it latent active. So just I chose this example because it's still, I mean, yeah, it is confusing, I agree. But I mean, because I wanted this relationship to the rock in the sense that the rock also reacts on the environment and the cell also reacts on the environment. But importantly, the reaction which they do on the environment is not of the type such that the sensory state which is coupled to the environment changes because of that. That's what I think for me is the important. It's the reason why I thought this was interesting. Because it does something to the environment, but sometimes the environment is, because it's a reservoir which is so big, you just put more into it, but it doesn't change. It's, if it's acidic and I put 50 more ions, it's still acidic. So so that's why I thought, and if I hit a rock and it puts more warmth in the environment, it still has the same temperature. So that's why I thought it's an interesting, because it's not only latent. It's also it also does something to the environment, which I thought was an interesting. But it might be confusing, yeah. But this was the reason why I chose this, because it shows this difference.
No, I appreciate that. And my feedback is really to try and tell you what is confusing and what is not confusing. I think what you've just described is very interesting. And if I was your age and writing this, what I would say is this is exactly the kind of assumption that 20th century physicists made in terms of a heat bath. So you assume your heat bath is always at the same temperature, even if you're generating heat or doing work. And under that simplifying assumption, you can then derive equilibrium physics and thermodynamic equilibria. So I think what you've described is very interesting. That's not how I thought, though. You wanted to use the notion of action that acts directly upon the sensory states, as you've got on the lower right-hand side here. I think that's distinct. What you've got with the cell here, you've just got a conventional Markov blanket where the active states are pumping ions in, they're changing the concentration of ions in the extracellular milieu. What you're saying is that the change is so small it won't be detected. Well, yes, and then you'll get equilibrium physics when the environment doesn't change. Effectively, you've got an isothermal heat bath, and then you've got classical physics. That's, I think, an interesting point from the point of view of self-organization far from equilibria. It's not interesting. The whole point of the free energy principle is it applies to systems that are genuinely open to, in the sense that they're in bi-directional exchange with the environment. And if there are no consequences of action because you've got an enormous heat reservoir, then that bidirectionality means you've no longer got that openness that is actually circular. So and that you wouldn't get reactive matter or active matter, or Turing pattern formation out of these systems. You just be working. So I think it's important that from my point of view, to avoid any, confusing the reader, I think you need to make a distinction between the situation here with the cell that is acting upon the environment, and it's just that the change in the environment is very, very small, so that there's no change in the sensory states. That's very different from the diagram at the bottom, where the active states directly change the status of the sensory states. That's a very different kind of action. So in this instance, there will be no change in the external states, but there may be a difference in the way that the sensory states affects the internal states. So the story I'm encouraging you to tell is, if you're a neurobiologist or a neuroscientist, this would be like selective attention or sensory attenuation. So that I can actively switch off the sensitivity of some of my sensory states without changing the world at all. So if I was looking at myself, if I was looking at a system doing this, nothing would change. So it would be completely latent action, but the action has a profound effect on the self-organization on the inside, because now I'm changing the signals that the sensory states are sending to the internal states. And this is a really important mechanism in cell biology and in cognitive neuroscience. In cognitive neuroscience, this would be attention or sensory attenuation. In cell biology, it would be affecting the sensitivity of certain cell receptors. So you could use something like voltage sensitive NMDA receptors, which have a profound effect on the coupling between the inside and the outside.
Yeah, I mean, so I understand you were saying, I think this also relates to the example which you said before about maybe closing the eyes or something. Maybe not totally, but like I think so. Okay, I'm getting carried away. So why I think this diagram in the right bottom is still correct is because yeah, it's a little bit, it's confusing, but the sensory, so the acidity in the cell, it was representing the external state until it became, it crossed a certain threshold. Then it is not representing the external state anymore. But it's not because it's attenuated, but it's because the acidity is being acted away. So that's why I mean it's not an attenuation, but it's really a change of the internal milieu through putting something, yeah.
Yes, but notice what you've done here. You've had to talk about the internal milieu. That's the internal states. What the argument, and you could certainly invoke all sorts of neurochemical, electrochemical, gene protein interactions that is doing the inference on the inside, but that's not coupling to the external states or representing the external states. That's just a process theory about the internal dynamics that are doing the active inference. So from the point of view of active inference and the free energy principle, what's going on the inside of the cell will never be known apart from the cell itself. All you can observe are the active states effectively, and I think your key point is that there are certain active states which an observer of the cell will never see, and yet it can have profound effects on the homeostasis and the intracellular dynamics. That's what you're saying.
Yeah, I guess you're right. Yeah, I guess that's really my main point. Yeah, I agree.
Which is not quite the same as the example with the ball. What I'm trying to suggest is I think there are a number of at least 3 different kinds of finessed treatments of active particles, which I think, that's what I meant by developing a more fine-grained ontology of different kinds of things, different natural kinds. So I think the ball is that's just a classical. Well, no, yes. Before we leave your slides, though, I just thought there's a couple of little things that would help in presentation or explanation to readers. So I like this expression number 4, where the partial derivative of free energy with respect to the internal states is equal to 0. And when I write down that kind of equation, I try to explain it to non-mathematicians by saying, basically, we've found the minimum of a free energy function. At the bottom, the gradients are 0 because the free energy function is flat. So one way of articulating that is that we can think of this as a solution of some dynamics that are performing a gradient descent and then finding the minima, at which point the gradients are 0. So that's one way of understanding minimization in terms of just natural dynamics of self-organization. But there's another way of understanding this. This natural kind of self-organization looks as if you're destroying the free energy gradients that create the dynamics, because in finding a part of the landscape where there are no gradients, you are effectively escaping and destroying the gradients that cause you to move there. And I use that phrase because that's a phrase that Hermann Haken used to use, this notion of vitiating or destroying the gradients that construct or create the norms or the system or the dynamics itself. So I thought that was a nice touch, that you're expressing the minimization or the optimization as a basically destruction of gradients to find the minima. Another little technical point here. You were probably trying to find the English words when describing the expression for the free energy. That second expression, so the expected log probability, the true probability, you can say to people, this is sometimes in machine learning known as the generative model, and it's effectively a joint probability distribution over the causes, here the external states, and the sensory consequences of those causes. Notice that in this instance, we've conditioned this generative model on internal states that parameterize Q and the current active states that are in play, generating or may or may not be affecting the external states. So just to clarify nomenclature there, so people in machine learning will recognize what you're talking about here. If I can, do you mind if I now share my screen just to take you through the different kinds of latent action or latent inference, active inference?
Maybe just one last question. I guess I was going to say that the second term was the predictive model, but I'm just confused because it's also the real probability distribution, right?
Yes, that's absolutely right. So the free energy principle makes that, this is an important conceptual point, which is a bit subtle but fundamental, which you may or may not come back to when thinking deeply about these things. The free energy principle describes systems that self-organize to their normal form or characteristic states. So those characteristic states technically they're called a pullback attractor or an attracting set. So it is these set of states that define, that just are the characteristic states or the states that characterize this kind of thing, which means you're assuming that the thing exists and will converge to its characteristic states. That just is the norm, the normal states that are characteristic of this thing. And then all the free energy principle does is say, if that is true, then it must be the case that you can write down all the self-organization as a gradient flow on the variational free energy, where the variational free energy effectively equates the generative model with the probability distribution over the attracting set, which is your norm. So the generative model just is a description of the attracting set of states or the characteristic states that your system will converge upon.
Okay. So the generative model is, so to say, the embodiment, which is the probability distribution in a way.
Absolutely, yeah. Now, in machine learning and simulations of active inference, you make a distinction between prior preferences and goals and norms, intended states, and the actual states of the world, and then you simulate it in the hope that you can simulate self-organization, active inference, and learning to the norms. But the free energy principle actually turns that on its head and says, from the point of view of physics, the very fact that this system is behaving as if it has these norms means that it must be described in terms of a gradient flow on this generative model. And the generative model is just a description of the states in which it exists, or the characteristic states to which it returns. So you're absolutely right. They're the same thing from the point of view of the physics.
This is so deep, like it feels like it's basically like probability theory. Like it's like if there's a true probability then in the limit you have to have this distribution basically, or the thing, or there's no probability, like, so this thing in the limit has to have like the thing, or there will be no thing. Like it's
yes.
And the thing is, so to say, just a very complex probability distribution. So yeah, that's
yeah, it's almost tautological. The free energy principle view is almost tautological, and it is deep, but it's also very, very simple. It just says, yes, if something exists, it must have characteristic states. Characteristic states are defined by probability distribution over the states to which the system is attracted. It can't be any other way. And that becomes your generative model. And then you just write down the equations of motion or the dynamics of this system that must be in play if this attracting set or characteristic states or norm exists. And that's and that is the free energy principle. So it's one of Dan Dennett's strange inversions. It's not saying to exist you have to minimize your expected free energy. What it's saying is, if you exist, you will look as if you're minimizing your expected free energy under a generative model, where the generative model is just a description of your characteristic states. So it is deep, but also very simple. Right. So that's, yes. So you've got all that there. Yeah.
I mean,
good.
Yeah. I would even say the generative model is even more than just a description, because it has to be a physical thing which is happening. So in a way, it has to be an instantiation.
Well, yeah. Well, yes. That's an even more subtle point. So of course, when you're observing something self-organizing, all you can see are the active states. So you don't actually know what the internal states are doing. So you're absolutely right. It looks as if the internal states are doing a gradient flow of variation free energy under a generative model, and that will have a biophysics if you could see it, but of course you can never see it, so you don't really have to worry about that. So the generative model doesn't actually exist from the point of view of somebody observing a self-organizing personal system, other than you can explain its behavior under a generative model by appeal to the free energy principle or active inference. But of course, you'll never know what's actually happening on the inside. You'd have to create some hypotheses, for example, about intracellular dynamics. And people do this a lot. So it could be that this belief propagation or this predictive coding or Bayesian filtering or model predictive control, lots of ways of looking at these gradient flows, is implemented by electrochemistry or kinetics of an intracellular sort, and start to have hypotheses about what's going on inside the cell. But from the point of view of the free energy principle, you'll never know, because as soon as you look inside the cell, you've destroyed the cell. So you can't you'll never really know. It doesn't matter though, because if your hypothesis is right, you can start to simulate cells, and you can simulate the biophysics and make predictions about how it would behave, and then test your hypotheses by looking at the behavior of cells and the motility. You can sort of put labels on the receptors, and and start to do standard science.
Yeah, I would actually really be interested in simulating rocks, to be honest. This would be like my point, to make it a little bit away from the philosophy, because I wanna grab everyone, I wanna make this into science. So I wanna simulate the rocks. Yeah, this would be my thing. So you can make some nice videos so people are happy. But yes, I still listen to all that you say. And there was one more point. Yeah, so before you delve into your papers, if I may, maybe just one last question. So because so this seems something which is very interesting to me, this idea that you say that the free energy principle, as you describe it, it needs to have needs to be bidirectional, in the sense that there needs to be an observer. I don't fully understand. So I mean, just because I cannot observe it, I'm probably misunderstanding some great thing. I'm just like, so in internal dynamics, like if we say, okay, the cell does some restructuring, which is not updating the internal model, but it's just really like fixing some internal stuff, and there's, like we said, it doesn't do anything to the outside world, which is interesting. Then you say, okay, although this might help the system to reduce surprise, or be closer to what it wants to be, or whatever, it's still not inference, and I don't, or it still doesn't fit into the free energy principle. And I don't understand why.
Oh no! It would certainly fit into the free energy principle. I mean, a simple example would be going to sleep, or just thinking. So you can minimize your free energy by minimizing the complexity term of the free energy, or the log evidence, simply by doing a lot of house cleaning on the inside. For example, reducing the acidity of the intracellular, removing, so changing things on the inside that you never see from the outside. So I mean, this, I think, will be an important example you should bring to the table. Is somebody who is asleep, or say in a coma, are they now inert, or what kind of, say they're dreaming, and you don't know, say ignoring rapid eye movements, for example. These are really interesting questions. What's the difference between a rock and somebody who is dreaming? So that will be one different kind of latent action, or latent active inference. So everything can be described in terms of minimizing variational free energy. Just open brackets, don't get too worried about sort of an observer of a particle, because just focus on the description of a particle or a person as if they were minimizing their free energy, and therefore the kinds of behaviors that you'd expect to see and hypotheses you can generate about the internal states. Otherwise, you really do get into map territory, observers of observers, and it all gets philosophically a little bit contentious, and you can easily get distracted. I think you've got a much simpler, more powerful story to tell here, observing the observer or measuring the measurer. So to come close brackets, so to come back to that, you can easily see that just by noticing that the free energy, if you rearrange your equation here, you can write it down in terms of accuracy minus complexity minus accuracy, where the accuracy is the expected log probability of your sensory states given your internal beliefs about internal representation, about encoding of beliefs about the causes of the external states. So if you take away the sensory states by this covert action, say on the bottom left, where A influences S by basically switching off the sensitivity of this sensory state, so that you now no longer can even report fluctuations in the external states. For example, as we go to sleep, we basically switch off the sensitivity of our sensory receptors, so we don't hear or see or feel, with the exception of the oculomotor system. Then that means that the accuracy term just goes away, but you've still got the complexity term, and therefore in a dynamic context you can always minimize the complexity, thereby minimizing the free energy or the model or the model evidence. And that usually means some kind of reorganization, some kind of homeostasis on the inside. And I use that word because you can then reference things like Giulio Tononi's synaptic homeostasis hypothesis, which is one example of what that might look like if you could actually look inside your head while you're dreaming. Of course, you can't. You can only sort of use neuroimaging or small animal models to test the hypothesis that you'd expect to see part of the internal homeostasis, very much like your cell here, doing a certain thing which would minimize the complexity of the implicit generative models that the cell or the brain is using. So that, I think, will be one kind of latent active inference or latent action, which is not the same as the ball bouncing back into shape, but it's much more, I think, appropriate for things like you and me, and possibly even cells, when they suspend their direct engagement with the environment just to resolve their complexity and to improve the generative models of the world, where improvement here is simply read as minimizing complexity or maximizing the model evidence so that they are fit for purpose when they open their eyes again, or when during the next day, or when the cell exposes itself again to the internal milieu. So it's not the free energy in the moment that's important, it's the path integral over the time that this system exists. So that's one, that's why I thought it was important you distinguish between the different kinds of latent actions, because certainly from the point of view of cognitive neuroscience and neurophysiology, and one could even argue cell biology, these kinds of latent actions are very, very important, and exactly as you're intimating, mean that you can't just say that something that doesn't move isn't doing some kind of active inference or latent active inference, because they could certainly be doing that. And you wouldn't know by looking at it, but you would know if you waited long enough and then saw it start to re-engage with the world, because you would have optimized your generative model, or the thing would have optimized its generative model while it was asleep, or while it was quiescent, or while it was hibernating, or while it was on the dark side of the moon. All of these things. I think are a testament to this notion of latent action, action on the inside, basically, or action in the lower left that is implemented directly, not on the external states, but on the sensory states, or how the sensory states couple to internal states. And we'll see briefly, you could even say that some of the internal states act upon Markov blankets within the internal states, and then you've got a very similar kind of covert or internal action that people normally ascribe to attention, and that in turn leads to a formulation of mental action, which I mentioned simply because of your day job in implementing global neural workspace theory. So one kind of action you could think about as part of a taxonomy of different kinds of latent actions is the kind of action that will be necessary for ignition in the context of global neural workspace theory. What does that mean? Well, it basically means that there are certain hierarchically lower or more peripheral or sensory bound inference, perceptual synthesis of a subpersonal, very low level, unconscious sort that suddenly get access to the global workspace. How does that happen? Well, that basically can be thought of as certain actions providing privileged access of lower representations to higher representations. And that is exactly the same mechanism that people bring to bear when understanding the action on the sensory states. Again, either attenuating or the influence of lower order representations on higher order representations, or augmenting them or selecting them in the spirit of selective attention. And if you're dealing with continuous state space models, this operationally is usually cast in terms of the precision. So the precision, say, of prediction errors in a precision weighted prediction error formalism is the thing that mediates the action, because you have to control the precision. So if you now have certain internal active states that are acting to change, to either attenuate or augment the precision of sensory states, or their associated prediction errors lower down in, say, a hierarchy, or on the Markov blanket, the outermost Markov blanket, then you've got a very nice model now of how it would be that certain sensory sets or perceptual sets ignite and gain access to the global neuronal workspace. And this is actively controlled through mental action and through what would look like attention. So that will be another kind of latent action that you could sort of put into the mix. So
did you write anything about this?
Yes, I haven't, but there are two of the papers I thought you might enjoy reading speak to that. Have we got one? Yes, one by Jakob Limnanski, who's a German colleague, who's written about this purely from the point of view of phenomenology, and he's particularly interested in. He's a cognitive neuroscientist, but is interested in inferring what we do and sensory attenuation and things like the rubber hand illusion.
But I mean, especially with respect to the global latent workspace ignition, which you just talked about, because I feel like this is super interesting to have this ignition related to predictive coding and some kind of latent sensory motor processing. I think this is very related.
Right. Well, I've put one paper up which was an attempt to try and formulate popular theories of consciousness under the free energy principle. And one important part was a reference to global neuronal workspace. Yeah, and I'll show you the paper. It's been rewritten for the Journal of Consciousness Studies by a gentleman called Chris Fields, with a different perspective. So the archived version, which I think you'll find more interesting, is not the same as what will eventually be published in the Journal of Consciousness Studies. But from your point of view, the archive will have all the necessary information in it in terms of references that you could cite along those lines. I can't remember precisely how much it goes into global neuronal workspace, but certainly I remember writing stuff, bringing together Mark Solmes's notion of felt uncertainty or felt precision and the role of the ascending neuromodulator transmitter systems with ignition in global neural workspace formulations.
Nice.
There is a technical paper which talks about that specifically, but I think probably from your point of view, it's probably best to just read this sort of archive paper and see what references have been used there, and then you can make your own mind up. Yeah. So that would be, I repeat, that's what I had in mind with lots of different types of latent action. It's not just the direct action on the sensory states, but also you could actually have nested Markov blankets. And as soon as you have nested Markov blankets, each nested Markov blanket has some active states that could be acting inside the cell or the brain on the external states, but the external states are still inside because you've got nested Markov blankets. So that's another hierarchical, literally deep extension of your argument. Which goes well beyond the bouncing ball. I think it'd be useful if you can just unpack all these different ways of how these structures could.
So I found I think through your explanation I just found actually an interesting difference between rocks and cells, and that is that rocks do not have the possibility to attenuate, to like close off from environmental stuff, like.
Yes. Yeah. Absolutely. Yeah. Yeah. I mean, and then you can, in at least in an at least heuristic way, you can start to say, well, look, what this argument would look like from the point of view of a cognitive neuroscientist or a neurophilosopher, is that this ability would look just like attention. So there's going to now be an intimate relationship between attention, as read psychologically, and the kind of latent actions that we associate with higher order life forms that cannot be possessed by a rock. And you can start to answer some of Robert's questions. Well, the difference between the rock and someone who's asleep is that the person is actively asleep because they've attenuated their sensory states or the sensory inputs. A rock cannot do that. Even though they're both sessile, and you wouldn't know by looking at them, there is something fundamentally different about the fact that this person has chosen to be asleep and has actively acted upon their internal states to disconnect, sequester themselves from suspend their engagement with the sensorium for a period of time in order to minimize complexity or minimize the variation of free energy. I'm probably over talking this. I think the best thing is if I just show you the papers.
It's fine. I mean, basically the difference is, I think, that there's one conditional hierarchy more. I mean, the stone is still attenuating. I think I was just thinking about this. I mean, it is attenuating its sensory thing through pushing it outside. But it's just not. It doesn't have a condition. It cannot. There's no mechanism such that there can be a second variable which decides if the rock will attenuate or will not attenuate. It will always attenuate, and I guess that's the difference. That there's no nested Markov.
Yeah, I think that's key. I mean, all you're saying is, well, take the stone argument or the bouncing ball argument, and then say, well, now let's think about this in the context of a deep structure where there are Markov blankets within Markov blankets, so that now action of this kind could be on external states, or it could be directly on the sensory states. But both the external and sensory states in the context of nested Markov blankets are both internal states, so that it's both latent. What would this look like? It would look like things like bouncing balls or sensory attenuation or selective attention. And as you say, it has to be actively prosecuted. You have to actively do these things. You can't go to sleep just by being a rock. You have to activate the right sort of or for sleep.
Yeah, but again, I'm careful with this. You have to act this way. It again sounds as if there is some Fristen, some infinite Fristen chain of Fristens, where some of these Fristen people say, "Now I'm doing it." I mean, it still has to be it still has to be a flow which automatic. I mean, it's still you know, it's still a automatic process. So that's why that's why I'm doing this whole thing, because of this this paradox, which is still not really which this idea of in what sense am I acting as independent? Yes. Yeah.
Yeah.
Okay, but maybe
yeah, I apologize. I spent a lot of my time talking to physicists and mathematicians, so by anthropomorphizing it, it sometimes makes it clear what I'm trying to say. You've got the opposite problem. You want to de-anthropomorphize it and to say, no, it's just self-organization. You're absolutely right. It's just, it looks as if, blah, 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 blah. I just I find it helps to explain to people who are not to get the intuition across. But you're absolutely right. That's why I always say,
this is exactly the point where I'm like, okay, so when is it actually, when is this change in state being like an emotional, like a conscious emotional change, and when is it not? I mean, this is really the
yeah.
Well,
that to a certain extent, that the last paper that I will show you tries to address that to a certain extent. Really? You can address it from many different perspectives.
Okay, let's dig into it then. I don't want to hold you back longer. You want to show me your stuff also.
Yeah, I mean, you're asking about phenomenology and self-modeling and self-awareness, and there are layers upon layers here. I suspect that in the first instance, though, you just want to stay close to the physics. And say that these will be necessary kinds of latent action to support consciousness, but you deal with that in another paper. I think that's probably going to be the simplest approach. Right. So where are we? Screen. No, let's go for screen's fine. Right. I'm hoping you can see this. So yeah, you've obviously read this paper. So this is the particular kinds paper. So this is what the equations that Robert was talking about. But what I wanted to, where's it gone? There we go. What I just wanted to know was that when you get into the literature on the various dependencies that define Markov blankets, they come in two flavors. For simple things that don't have action at a distance, they normally look like this, where the active states are hidden from the external states by the sensory states. So this would be good.
Okay, that's okay. I thought that was a mistake or something. Okay, okay. Please continue.
Right. No, there is another paper, but I think you don't need to look at it. All you need to know is that there are a number of canonical forms for Markov blankets that are defined in terms of the sparsity of the coupling. This is one canonical form, and then this is another canonical form. This canonical form is usually appropriate for active matter and simple systems where there is no action at a distance. So this will be good, for active matter or for ensembles of cells, for example. And in this instance, as you see, the active states only affect the sensory states and are affected by the sensory states. They don't directly communicate with the external states. So this is would be okay, for example, simple forms of cellular self-organization, whereas this normal form has the active states actually directly acting upon the external states and possibly the sensory states in the way that we've been describing. But I just wanted to make that distinction because I think you could put you want to put your rock here. I would put a ball here, and make the point that the outer surface of the ball could be the sensory states, the inner air pressure could be the active states, and the internal states could, no, but I'm not quite sure. But, usually as you actually showed in one of your simulations, the active states just lie underneath the surface of the sensory states. So you could have the inner rubber tube of a ball, a leather, say leather football, the internal states being the inner air pressure, and the external states being the leather surround. Now, this, that would be, I think, a suitable setup for a bouncing ball. And I think the key point you want to make is
no, I don't like it. I don't like it. Sorry, because you have two compartments. I want a homogeneous thing like a rubber ball. I don't want two compartments. That's too complex.
Okay, right. So the thing is, with homogeneous, what you basically mean is you've actually got an absence of long range connections. So you've actually got a whole nesting of Markov blankets as you get into the. But you can certainly have it as homogeneous.
Yes.
The point being made, the point I think you need to make here is that the ball or the sponge or whatever you want to use knows its normal form, and when perturbed or squashed or distorted by exogenous or external forces, will respond by returning to its normal form. And it can do that with this latent action that is not directly on the external states, but either on the sensory states or indeed on the internal states. What I think you need to make distinct, though, is that the attracting set, the norm for things like balls and plastic rocks, is a point attractor. Whereas for biological things, the attractor has it's an attracting set that has an itinerancy to it that by definition means that the attracting set has conservative dynamics, which means it has to have rhythms. It has to have solenoidal component to the attracting set. So there has to be some kind of biorhythm, whether it's a sort of oscillation at a very fast time scale or at a very slow time scale, reproduction or replication. There's another axis of distinction here, which I think you need to bring to the table, which is, are you talking about an attracting set, which is a point attractor? This ball has this shape. So this would be like homeostasis with a single set point temperature equilibrium point. So it doesn't matter, say I'm a thermostat and I perturb the temperature, then I will always bring my temperature back to my set point. I'm a ball, I squash it, and it always comes back to its set shape. So these are things that could probably be described as active particles in the way that you meant, in the sense that action is just influencing the sensory states or the internal states. But crucially, these kinds of things have point attractors. They have equilibrium points, and their non-equilibrium steady state is actually an equilibrium steady state. That should be distinguished between biotic self-organization, where the attracting set now is quasi-periodic or chaotic, and that quasi-periodic or periodic or chaotic attractor means that you will have a recurrence, you'll have a solenoidal flow, you'll basically have biorhythms and life rhythms and dynamics that are mathematically those you'd associate with autonomous dynamics. So that would be, I could have put a ball in here, but I put a cell in here, but implicit, so and the two kinds of things would be very, very different, and that's what I was meaning before. I think you could tell a good story here by making this a much more refined ontology. That with this kind of setup, this canonical form for the Markov blanket, you can go in two directions. You can either have an equilibrium set of norms or attracting set, or you can have a periodic or chaotic attracting set with non-trivial conservative dynamics. And that takes you to biological self-organization. In a similar way, I think you can sort of take the other canonical form here, where you've got the direct action on the external states, but no action on the internal states, which leads you to planning and strange particles. But you can also do this either with just a single level or with multiple levels, which take you into the world of this ignition and Markov blankets within Markov blankets. You can even describe in terms of axis neblox, axis consciousness. You've got sort of different levels that you can deploy the same dynamics. So I think a diagram like this, but actually unpacked in much greater detail, I think will be very useful for the reader. Just building upon something like this, but saying, you can either have a point attractor or a chaotic, an itinerant attractor, and these would be sort of non-biotic, self-organizing active particles like like bouncing balls and active matter. Whereas these ones will be oscillatory and have biorhythms and life rhythms, and you could, things like so these things would be like thermostats, and these things would be more autonomous and have rhythms such as cells and viruses, for example. And then you move on to these kinds of things, which are more like you and me, that could be very shallow or they could be very deep. And if they're very deep, you've got an interesting now action on sensory states inside actions on sensory states, because you've got this nested Markov blanket structure. So that's what I was suggesting as the next stage of this ontology of natural things and natural kinds that you could leverage. This is a technical paper which really tries to introduce these different.
But then, can you go back to the paper before?
No, I've just deleted it deliberately to force myself onto the next one. You can think about it. That's your job. I don't need to worry about it. This paper, if you're interested, it just explains the key difference between systems that have the very simple systems that just have these fixed point attractors like bouncing balls and rocks, plastic rocks at least. And stochastic chaos, and I think it had the sort of derivations of the normal forms for the different kinds of Markov blankets you can get and how you can experimentally detect them. But I don't know that you're going to get very much from this paper, other than to appreciate the importance of what's sometimes called conservative flow, also called solenoidal flow, that characterizes non-equilibrium systems that break detailed balance, which are things like cells, as opposed to dynamical systems with a Markov blanket, but don't have this solenoidal non-dissipative dynamics and have point attractors, and they don't break detailed balance, and they're time reversible, and they have thermodynamic equilibria as opposed to being non-equilibrium. And I think your balls and your thermostats are these that don't have that don't have this solenoidal flow, and therefore they don't break detailed balance. So I think that's an important distinction that you need to bring to the table to have a full repertoire of different things you can talk about. So this is the most detailed.
But I don't fully understand this no time reversal thing. That sounds
There's a lot to understand, and as you get older, you will see all these things in different ways of looking at the same thing. This is being recorded, so I'll just say this one more time, and then you can go away and think about it. There's a bright line between two kinds of systems that can be articulated in a number of ways. The bright line is basically whether you've got purely dissipative dynamics or whether you've got conservative dynamics or non-dissipative dynamics. The distinction between dissipative and conservative is due to something called the Helmholtz decomposition of the flows of the dynamics of any self-organizing system. In the absence of the conservative or non-dissipative flow, you end up with traditional equilibrium physics that is characterized by a fixed point or equilibrium point leading you to an equilibrium steady state of the kind you'd have done at school in terms of classical thermodynamics. Technically, these systems do not break and therefore have detailed balance, which basically means because they're all converging to a fixed point, at the fixed point, you can reverse time, and there is no difference between the system running forward and backwards in time. On the other hand, for biotic self-organization, for
macroscopic variables, for mean field variables, yes.
Yes. For the other kind of dynamics is where the dissipative part is very small in relation to the non-dissipative or the conservative part. These systems have non-equilibrium steady states, and they wander around. They don't have a fixed point attractor. They have what's called have an itinerancy or a space-filling attracting set. This technically is known as systems that break detailed balance, in the sense that it matters whether you're going forward or backwards in time. So if you think about something like a swimmer that has a rhythmicity, you can tell by looking at somebody swimming whether the video is being played forwards or backwards in time. Whereas for systems that are that are at equilibrium, you can't tell. You don't know when a system is at equilibrium whether your movie of this system is running forwards or backwards in time. So I just said that so you can go through the the recording and try and think about examples and look at the literature. They're just different perspectives on the same thing. I think you need to make that distinction, because actively maintaining either these equilibrium or non-equilibrium steady states would look very, very different. So the rock and the ball are examples of maintaining an equilibrium steady state because they've got a fixed point attractor, whereas the cell and the people and the biotic self-organization would have a different kind of autonomy that inherits from a conservative, circular, solenoidal, itinerant kind of dynamics. I think that's an important distinction between biotic and non-biotic, which is orthogonal, I think, to your notion of active versus inert. It's another axis I think you need to put into the equation. So now let me go straight to this one. Before I do that, I was.
Yeah, maybe it's orthogonal. Yeah, it's okay. Sorry, I don't want to. Maybe it's orthogonal. Yes.
Yeah, I think it is orthogonal because well, if it's not, at least it's nested. You'll have to think about that. Okay, that didn't work. What am I trying to do here? So this is the paper I think you'll probably find most useful from the point of view of global neural workspace. Let me just see if I've got the GNW. I'm not sure this is going to work. Global. That's right. Global. I'm pretty sure that. Yeah. Okay. Well, actually, it's not. Might be not neuronal, but certainly it was meant to be neuronal. In particular, it sort of highlights this notion of internal action as covert, and difference between overt and covert action by deploying the precision or the gating of various sensory representation or prediction errors that gain access to higher and higher and higher nested Markov blankets. So I thought that would be interesting for you for two reasons. One, this is a kind of covert action, and two, it may speak to your day job about simulating global neuronal workspace theory here in the instance of
can you scroll up a little bit, Carl? Oh, sorry, I just didn't see the whole picture, the figure. That was all.
All right, sorry. There.
Yeah, I might start working with a guy in Italy who has the dynamical representation and the MEG analysis thing, where he found that people that you actually can measure that abstract concepts are fired before the actual action is fired. It's very interesting. It looks very should be a nice mapping to a lot of this.
Good. I see what's happened. So it's gone over here. I don't know why it's done that. I just so this is the gentleman Limanowski that I mentioned. So
Yeah.
this is more about phenomenology. It's nothing to do with really with what you'll be writing about, but it is taking this notion of actively setting the gating on your sensory states in a nested context, as equipping you with mental action and what that means for phenomenal transparency and the like. So this is not a canonical paper. It's just, I thought, an interesting example of how you could take your latent action into the space of phenomenology, should you want to. The key author here is Jakob Limanowski, who's not a student of, but certainly sympathetic to the work of people like Thomas Metzinger and a lot of Thomas Metzinger's colleagues. So I just bring that to the table there, just we've done this stochastic chaos, and then finally, it struck me that one way you could sell your latent action is in terms of direct action, in the same sense that Gibson tried to talk about direct perception. So I don't know if there is a notion of direct action, but what's this thing? Session time now. Yeah. So I just grabbed. This is just one of 101 papers on direct perception, direct visual perception, for example. It just struck me that your latent action was if you like, the complement or the inverse of direct perception, that you're actually putting all the action on the inside, as opposed to all of it on the outside in the Gibsonian sense. So I put this paper out really just to, incite you in terms of thinking about how this kind of internalized action or covert or latent action would fit with a purely inactivist account, and whether you can steal some of their favorite phrases to promote latent or covert action. And that's it. So I'll stop sharing now. There we go. And it's just you and me left. And now I have to go to my next meeting.
Oh, wow. Okay. Yeah, Karl, I thank you so much. It's just a pleasure to hear you talk. And not just that was not cool. It's a pleasure to interact with you. Like it just feels it's very it just feels like some, I don't know, like a flow, like something is interacting, which is very nice that it's interacting. It's very, yeah. I don't understand everything you say, but yes, a lot of stuff I understand, I think, and this is good. Okay.
Yeah, it's just to make you think, and also to make you think about how your readers will respond to the way that you think. Well, let us know. I'm going to stop the recording, and then I think Robert will send you the recording so you can go through and think about what was said and your responses and the like. And but feel welcome to contact Robert again and let us, if you'd like to have another session in a few months' time, depending upon how your machinations go, you'll be very welcome to come back and tell us what the progress has been made.
Oh wow, okay. Yeah, cool. Thank you, Carl.
Okay, I'm going to stop the recording. Brilliant.